we're going to look at now some physical properties of elements and trends in those physical properties across the periodic table. So there are really four that we're going to be pretty interested in here. One is atomic radii. How big are the atoms and how do those sizes change as you move through groups and periods on the table? First and second, ionization energy, a thing called electronegativity, and then we're going to look at the size of ions. What happens when you gain or lose electrons to the size of an atom. And so we're going to be looking at various trends across the periodic table within groups of elements, across periods of elements for these four concepts. But before we can get there, we have to understand two ideas. And those ideas combine to form what is called effective nuclear charge. And the first of those two ideas is nuclear charge, which is essentially the attractive strength of the nucleus. How big is it? If you have a large positive charge in your nucleus, you have a large nuclear charge. Smaller elements that have fewer protons in the nucleus have a lower nuclear charge. So pretty straightforward on that. Beryllium has 4 protons in the nucleus, 4 electrons, 1s and 2s. And so we would consider its nuclear charge 4+. The second idea that we need to look at here is called electron shielding effect. Essentially the idea here is that electrons in the higher energy levels do not feel the full effect of the nucleus because there are electrons in the lower energy levels shielding them. And so if you have any more than one electron shell, then you have electron shielding. So essentially we're looking at anything beyond the first period is going to have electrons in the 1s and then electrons in other energy shells. And so here's another image of what this looks like. Here you have electrons in different energy shells. They all have this kind of positive attraction to the nucleus, but the outer electrons, that positive attraction is being mitigated by the repulsion of the electrons in the lower energy levels. And so what is effective nuclear strength? Well, it's the positive charge experienced by electrons in any polyelectronic atom, more than one electron. That results from electrons in the outer energy levels being shielded by electrons in the inner energy levels. This is not a simple arithmetic process. By that I mean that beryllium atom on the right side of our screen here, the electrons in the higher energy shells don't feel a 4+ charge because those electrons are moving all over their energy fields and they're not strictly additive. And so this is actually a table here of effective nuclear charge. And so you can see that these are all decimals, right? So they're not whole numbers, subtractions. They are portions of charge felt. So there's our beryllium atom there in, let's see, the second row there. It's got a Z number of 5. And then you look at the 1s electrons. Z number of 4. So we're looking at BE, not B. And you're looking at those electrons in the 1s do not feel that 4 full plus because they interfere with one another. The electrons in the 2s looks like they feel a little bit less than a 2- charge because all the three other electrons are interfering or shielding the 4th electron from the nucleus. So there are some tables of effective nuclear charge. Okay, so now let's put those into practice and let's look at our first idea here in terms of physical properties, atomic radii. So we might ask some questions. How big is an atom? Well, when you had a Dalton atom, when you had a plum pudding atom, when you had a Bohr model, it was very easy to answer this question. Particularly with the Bohr model, the atom was as big as the largest electron orbit. But when electrons are no longer orbits, but they're energy fields, it gets a little bit harder to figure this out. And when we think about them in constant random motion, when we're thinking about them as particles, we have kind of a follow-up question here. Is an atom always the same size? Because what if that electron does that? Now that atom's size is wherever that furthest electron is. But that electron makes that move, well, then the atom just shrunk. And so how are we going to measure an atomic radius when an atom does not have a constant size? And so scientists have essentially generated a trick, a method for getting a repeatable measurement that we define as atomic radius. And the definition is this: half the distance between the nuclei of any adjacent atoms. So this is actually a pretty clever bit, right? We're not actually measuring the electron clouds. We're assuming that if we have two atoms in crystalline structure, they're in their solid structure or bonded together somehow, and we can measure the distance between their nuclei, then we can in fact then cut that in half and take that to be the atomic radius. And here's the thing: when you do that measurement through a process called crystallography, you find that that measurement is the same every time. So even though atoms floating around in free space may not always have the same size, when they are measured with this method, they do in fact always have the same size. And so now we have a way to make some comparisons. So we're going to talk about a couple of things here with respect to the table. What happens when you go down a group on the periodic table? Well, hydrogen has its furthest electron in the 1s, lithium in the 2s, sodium in the 3s, and each of those has their highest energy electron in a higher energy level, and higher energy means further away from the nucleus. So in a completely unsurprising turn of events, atomic radius increases as you go down a group. Now, let's talk about going across a period. This is a drastically different thing. So your first thought might be, well, as you go across a period, then you're increasing your number of electrons, so the atom must get bigger. But we have two things going on here, right? You're increasing the number of electrons, but you're also increasing your nuclear charge. Each nucleus, as you move across, let's say the second period, gets bigger and bigger and bigger, and so can hold electrons tighter. And where are those electrons going? Well, every electron in the second period is going into the second energy level. So there's not a significant increase in shielding, but there is a significant increase in nuclear charge. And so actually, as you move across, you're going to see a decrease in the atomic radius as you go across a particular period. So atomic radius decreases as you move from left to right. It increases as you move from top to bottom.